Hello friends, welcome to section 5 of the Hard Surface Modeling series. Now that we know the basic concepts and ideas behind the crease plus subdivision workflow, we can move on to learning about more advanced modeling techniques and tools. In this section, we will learn about localizing topology, a modeling technique that allows us to add more geometry in specific areas, without influencing the density of the rest of the mesh. This is extremely useful when working with a subdivision workflow on hard surface models, as you often find yourself needing more geometry but not wanting to add loop cuts or apply subdivisions. Understanding this topic will also advance your understanding of edge flow and poles, which we discussed the importance of in the last two sections. So let me start by explaining what localizing topology means, then I will tie it back to the rules of the previous section, looking at examples along the way. Over here I have a simple setup, a long, snaking set of planes, with a cylindrical cut at the end. To create the cut, I needed more geometry, so I subdivided the last plane, giving me 8 vertices to work with instead of 4. The issue is, one of the extra edges created when subdividing is attached to this plane now, making it an n-gon. To fix this, we could add an edge loop running down the mesh, and then connect the vertices, but by doing that, we add a lot of unnecessary faces. It might not seem like much, but in a subdivision workflow, this could amount to hundreds of useless faces, making our model more computer intensive. Realize that by adding this loop, we are essentially taking the resolution at the most detailed part of our mesh, and raising the density of the rest of the model to match. This is hugely wasteful and inefficient. Instead of raising the resolution of our entire mesh to the most detailed part, let's learn to isolate the resolution of the most detailed part, allowing us to have varying levels of resolution within a singular model. This is where localizing topology comes in. Our goal is to make a transition from this edge to this edge, during which the density transitions from 2 vertices to 3. We do this by taking the extra, middle edge, and diverting to the side. Press the K key to activate the knife tool, take the middle edge and cut halfway down, then divert it 90 degrees left or right and press enter. We have diverted the extra edge. But now we have an n-gon here. To fix it, we simply join these 2 diagonal vertices, turning the 6-faced n-gon into 2 quads, and have successfully transitioned from 2 edges to 1. Let's quickly go through more examples of localizing topology with 1 extra edge, before moving on to learning how to localize topology that has 2 extra edges. If we simplify the issue, it comes down to this: a plane with an extra vertex. In the same way, I can cut it down, and then left or right, joining the diagonal edges. This is the method for localizing an extra edge. Notice how the ratio from the low-resolution side of the plane to the high-resolution side is 2 to 1, which makes sense. Since we went from 1 edge to 2, the resolution has doubled. It is important to consider which way you want to direct the cut. In this case, I have an extra vertex here and here. Cut down, and direct each one inwards. Remember, we are trying to localize the topology. If I directed the cuts to the outer edges, I'm not really doing much apart from adding more faces, as I still have the issue of the extra vertices existing. However, if I direct them towards each other, they can meet up in the center, allowing us to keep the lower resolution edges on one side, whilst also having the higher resolution geometry here, all with great quad topology. This time we have a plane with 2 extra vertices. To localize 2 extra vertices instead of 1, the method is similar. Cut each extra vertex downwards, then connect them, and join the diagonal edges. Notice how if I cut the shape in half, this is actually the same method as localizing 1 extra edge, but mirrored to achieve the effect twice. If you extrude each side out to make quads, you can see how the ratio of the resolution is 3 to 1, which once again makes sense. Since we went from 1 edge to 3, the resolution has tripled. I found that in hard surface modeling, the most common and useful localizing techniques are with 1 or 2 extra edges, but when creating organic models like humans, it is useful to know how to localize 3, 4, or even 5 edges. Once you know how to localize 1 or 2 extra edges, you can stack the 2 techniques to localize any number of extra edges. For example, if you want to localize 3 edges, we will need to localize 2 times, the first time adding 1 edge, then again adding 2 edges, totaling 3 extra edges. If you want to localize 4 extra edges, you will also need to localize 2 times. Only in this scenario you will need to localize 2 edges twice. And if you want to localize 5 edges, you need to localize 3 times, twice with 2 edges, once with 1 edge. Once you understand this, you can localize any amount of detail. Let's see an example where we want to localize 3 edges. Remember, we are working our way up, starting at the bottom, where we have 1 edge, localizing our way up to where we have 4 edges, adding 2 edges in the transition. Since we will need to localize twice, let's cut this plane in half, performing 1 localization on each side. Subdivide the middle edge once, to turn this plane into a 5-edged engon. Now we can localize this 1 extra vertex by cutting it down, then to the side, and join the diagonal edges. The second half now has 2 edges on one side and 4 on the other. We know how to add 2 extra edges, cutting each extra vertex down, then connecting them, and joining the diagonal edges. The final edge can run straight down the middle. Now that we have gone from 1 to 4 edges, we have enough topology on one end to model intricate cuts, while the rest of the model stays in low resolution. You might have noticed that the process of localizing topology looks similar to insetting faces, and you would be right. Look at this object made of 3 connected planes. There are extra vertices here and here. Let's localize them by cutting each one down. This time, we don't need to change their direction left or right, since they naturally run into each other, and let's join the diagonal vertices. Now if we take an identical mesh and inset this face, pressing the B key to ignore the border, we can see it is applying the same effect. The similarities between localizing topology and insetting comes from the fact that in both the localizing technique and the inset tool, we are adding a diagonal edge, which lets us add quads within a face, at the cost of turning this vertex into an E-pole, as it is now connected to 5 edges. Combining this technique with our knowledge of diverting poles with supporting loops, localizing topology becomes the best option for adding isolated density in complex hard surface models. It is important to remember, as I have been stressing, that localizing is a technique whilst insetting is a tool, just like how Booleans are a technique whilst the loop tools, circle tool, as the name suggests, is a tool. Tools are just pre-made functions that simplify the process, instead of having to manually create insets or cuts in your objects. But if you learn the fundamentals of the functions, or techniques, the tools are applying, and their benefits and weaknesses, you learn the ability to manually recreate the tool, which, as we have seen with Booleans, subdivisions, and localizing topology, is more complex, but gives you much more precision, accuracy, and control. For example, insetting might include localizing topology in its function, but by knowing how to localize topology manually, you are able to become the inset tool, only with far more control. You can decide how much more resolution to add, where to add it, and the direction of the extra edges. The reason this video series is so focused on teaching you how tools work so that you can manually recreate them is because the future of Blender, and 3D modeling in general, seems to be heading towards a hyper-customizable, node-based workflow. Already in Blender, we have the ability to create our own editing tools, a feature added in Blender 4.0, and along with geometry nodes, is at the forefront of the Blender team's focus. By understanding the fundamentals, this video series is not only teaching you hard surface modeling, it is also teaching you the mindset required for the future of node-based 3D modeling. Now let's discuss when we should and shouldn't use the localizing topology technique, before looking at some final examples. Just like adding loops or applying subdivisions, localizing topology is a technique to add resolution to our mesh. However, it is more complex because it requires mastery of modeling skills and understanding of quad topology. When wanting to add topology to your mesh, this is the order in which you should be thinking. 1. Do I only need to add topology to my mesh in order to achieve more resolution in an isolated area, for example for a cut or extrusion? In this case, consider how you could localize topology and add resolution only in the isolated area. 2. Does my model need more geometry to keep its shape intact independently of a subdivision modifier, or does my model lack geometry along entire edge loops? Is edge flow being disrupted? In this case, consider adding loop cuts to add topology to increase the density of edge loops in your model. 3. Is the lack of geometry in my model preventing me from adding detail in general? Am I relying on the subdivision modifier to determine the shape and curvature of my models? In this case, consider applying a level or 2 of subdivision to add general density to your model. Remember, you can preview how applying the subdivision will look by turning off the optimal display option and switching to wireframe view. Localizing, edge loops, and applying subdivisions each adds geometry in a respectively higher scale and control. Localizing is the lowest in scale and highest in control, whilst applying subdivision is the highest in scale and lowest in control. Remember, just like all these techniques we have been learning, these can be stacked. You could apply a subdivision, but still feel one area needs more resolution and localize topology. Or you could add edge loops and then apply subdivisions. This is what I meant when I mentioned that this workflow is similar to a game of chess. Before each move you make, all these options are running through your head, and only you can pick which one you think is the best option in the short and long term. Sometimes you make mistakes, but through practice, you are able to recognize situations, and picking the best option becomes second nature. Now let's learn when you shouldn't localize topology. The main downfall of localizing topology appears when you are working on curved surfaces. In this example, I have two extra vertices here and here, so let's localize them quickly, cutting each one down, connecting them, and joining the edges. With a subdivision applied, you can see this has left a slight dent in the cylinder, which is caused by the localization changing the flow of these horizontal edges, which dictate the shape of the cylinder. The vertical edges are also being diverted, but remember, on cylindrical or circular surfaces, the shape only becomes skewed if the loops from the bottom face to the top face are skewed, not if the loops circumnavigating the cylinder are skewed. And in the case of this object, the localized edges going from the bottom to top face are skewing the shape of the curved surface. Using the three options from earlier, we can decide how we would be able to add geometry to this model. We can't localize, because it skews the shape. We can't add edge loops, that would also skew the shape. By adding more density to one part of the cylinder than the others, it ruins the circular flow. Our only remaining option is to apply a subdivision. Remember to clean up the result and add another subdivision. The main takeaway is that localizing topology disrupts curves with evenly distributed points, as adding geometry in an isolated area disrupts the even flow of the points. Let's look at a practical example before moving on to the final exercise. Here I have a mechanical piece mirrored on the X and Z axis to create this interesting design. In edit mode, you can see everything looks great. The creased loops all have good neighbors and edge flow, and are easily selectable. The shape is fully controlled, the subdivision is only here to smooth, and the tactful decision has been made to leave this face as an n-gon. The only thing it's missing is a circular hole in these front faces, which would allow this mechanical piece to connect to another piece. These are flat faces, so I can use the circle tool to cut a hole. However, it has a very low resolution of 6 vertices, and my design states this needs 10. The first thing to consider is where we can place these extra 4 vertices. If we place them on the top and bottom of the two faces, that could work, but when using the circle tool, you can see these edges are too stretched, as the original geometry is way too rectangular. Rather, we should place the 4 vertices on the left and right of the faces, to create a more even quad topology for our hole. After positioning our hole, we now need to localize the 2 extra vertices on each side. As shown earlier, we should avoid doing it on these curved faces. Instead, let's go to the nearest flat face and do it there. As practiced, I can cut each extra vertex into the middle of our flat face and connect them, then join the diagonal edges. Since we have good supporting loops here and here, the E-poles we created from the hole and localization do not disturb our edge flow and are in a safe position. Let's do the same for the other side, cutting the extra vertices, connecting them and joining diagonal edges. And there we have it, the high resolution area around the cut, without disturbing all these surrounding faces. Notice how we have altered the flow of the geometry in this area. The diagonal edges redirect the flow, containing and isolating the higher resolution geometry. Finally, with all the new knowledge we've gained in the last 2 sections regarding modeling techniques and localizing topology, I suggest you repeat a version of the exercise explained at the end of section 3. Instead of starting with one large subdivided plane, begin by spawning in a plane, extrude it, and localize some more resolution. Keep extruding and localizing to create more geometry. Start adding cuts and extrusions to add another layer of depth to this exercise. Make sure to keep varying your techniques. There are so many ways to perform the same action. Start extruding in 3 dimensions to increase the difficulty. This section was dedicated to learning about advanced modeling techniques. The next will be focused on learning about advanced modeling tools. With techniques and tools combined, the Crease Plus subdivision workflow for hard surface modeling becomes an insanely powerful method. See you there. Remember to like and subscribe for more, and comment any thoughts or questions.